Welcome to this first recorded video for the Part B lecture notebook of Module 4 on some useful applications of Modules 1 through 3. So this lecture notebook will focus on numerical integration. In this notebook, we will use NumPy as NP to do most of our computations. We will use matplotlib for a lot of plotting, and we will use polygons and rectangles within the patches of matplotlib in order to annotate our plots, much like we used some arrows to create annotations in the root finding lecture notebook that was part A of this fourth module. We will also use interactive widgets to help all of our visualizations, or quite a few of them, kind of come to life. So I won't go over this part as we've seen it before in the Part A notebook, but you should read through again very quickly to remind yourself, especially about the idea of calculus concepts, meaning calculus isn't a prereq for this class, and you don't need to understand calculus to understand and follow the narratives. It does help. I'm not going to say it doesn't help, but you don't need to know it. What we're going to do is focus on big picture ideas and use interactive graphics to help us explore these ideas and build a conceptual understanding of what calculus is doing in terms of numerical integration and how to apply the code and modify code that I give you to solve various numerical integration problems. So you should read through these learning objectives and these larger kind of objectives that occur by design of activities just to help orient yourself on what you're going to see. But in the interest of time, I'll just kind of go ahead and start. So this first recorded video will cover the basic concepts of integration, what integration is and how it arises. And we'll go through some of the geometric rules, including rectangle rules, in this first video. And then there will be two other videos that go over Monte Carlo integration and how to do Monte Carlo integration when the sets we're integrating become very complicated. This notebook, I expect, should take people between 6 to 9 hours to complete, and it might take on the longer side for quite a few people. So what is integration and why should we care? Well, what the integral of a function means can depend quite a bit on the context, which also helps to explain the why of an integral. So typically it refers to transforming a function into a scalar quantity that describes some type of important aggregate behavior of the function over a set. It is kind of like summing up the behavior of a function over a set in order to make important inferences. So I provide plenty of examples here. The one we're going to focus on that is perhaps the simplest and helps us build intuition is a physics-based problem where we use integrals to determine important quantities like velocity, which is given as the integral of acceleration, or more for the purposes of the examples I show below, displacement or total distance traveled, which involve integrals of velocity or the absolute value of velocity. There's additional examples here, and I encourage you to read through them, and perhaps even write additional ones you may be aware of. This was not meant to be an exhaustive list, is what I'm saying. So first, some notation. There are a few different notational conventions you will come across for integrals. If you start looking on Google or Wikipedia, you'll find a good number of different conventions of notations of how to express integrals. We're going to use a simple one. So suppose that we have a function f of x, and we have some subset of its domain that we call a. And that's the subset that we want to integrate the function over. Well, then we would simply write the integral. This is how you should read this notation. The integral of the function f of x over the set a. So in Markdown, it's very simple to write. You have this \int. It produces that elongated s. That's kind of like for summation. I have a as a subscript of that integral. That's the set I'm integrating over. And then I just write f of x after I put a space right there. And that's what produces this notation that you see. And that means the integral of f of x over a. Now let's consider a standard motivating example. We are going to avoid any and really all complicating calculus details, but we will build intuition by considering some simple examples involving the integral of velocity. So here are some general details. Suppose that we use v of t to denote the velocity of an object that is moving either forward or backward on some path over a time interval t naught to tf, where t naught denotes an initial time and t sub f denotes the final time. That's a fairly standard notation for initial and final times that you will come across either in calculus, physics, or differential equations classes. Suppose we are interested in how far along the path the object ultimately ends up relative to its starting position. This would be the displacement relative to the starting position. This is given by the integral of velocity. So here's some examples with intuitive solutions. I should say the integral of the velocity over the time interval. So imagine we could take some simple functions where we can intuit the solution with little difficulty. Basically, we don't even have to refer to anything from calculus to figure out what the answer is for what this integral should be, if this integral is indeed giving the displacement. So suppose the object's not moving, meaning the velocity is 0. Well, then the integral of v of t over the time interval should also be 0 because the final displacement of the object from its initial position is 0 units of length. It didn't move. That's not surprising. Suppose now that the object moves with a velocity 5, and I'm ignoring units here, so maybe miles per hour, maybe feet per second, just some units of speed 5. And that's meaning it's moving in the forward direction, and I'm having it move at that constant velocity for half the time interval, and then it immediately switches directions. It has a negative sign here, so it moves in the opposite direction at the same speed, but in the opposite direction, negative 5 here, over the last half of that interval. Well, then the integral of that is going to be 0 because the object just did a simple round trip and it ended up back where it started. So what should the displacement be relative to its initial position? 0. It didn't move relative to its initial position. But you might say, well, that seems kind of strange because it did move, but I'm not tracking the total distance it moved. I'm just tracking its total displacement when I integrate the velocity. If I want to know the total distance, then I should integrate the absolute value of the velocity because then that starts to give me the speed. So if you integrate the absolute value of the velocity over the time interval, then that will give you the total distance the object traveled. So now it helps to consider units. So imagine if you were moving in units that it was miles per hour, and if you had a velocity that was constant, all you have to do is multiply by the total number of hours that the object was moving in units of miles per hour, and the hours would effectively cancel out, and you'd be left with the miles, how far it traveled. So in this example, the integral of the absolute value of the velocity is equal to 5 times the measure or length of the interval. The measure of this interval is its length, and it would be given by the difference between the endpoints, t sub f minus t sub naught, t sub 0, which is called t naught, excuse me. So let's visualize these last two results. Here I define a function. I'm going to assume that t naught is 0 in this function. And in that function, I am assuming that I give this function an array of times, and then I give it what the final time is for computational purposes. And then I create an array of zeros of the velocity, and then I populate it with values. For each I in the range of n, I look at t of I, and if it's less than t sub f over 2, so it's in the first half of the interval, then the velocity is 5. And then otherwise it's negative at 5 because that means the t values are greater than or equal to that value. So let's create that function. And now all I'm doing here is defining the limits of integration, so 0 to 10. I'm just defining these as I want. So t naught will be 0, tf will be 10. This is using the default number of points to create a regularly spaced set of points from t naught to tf. I'm then instantiating a figure, and then I'm going to make some plots. I'm going to plot t, and I'm going to plot the absolute value of t, because that one, I know what this answer is. So it should be 5 times t sub f minus t naught, 5 times 10 minus 0, 50 should be the answer. And I'm just doing everything else after this is just for graphing. So I'm plotting this curve of the absolute value of the function as a red line that's slightly thicker than the default choice of line width. And then I'm setting the y limit to just be 0 on the graph so that the graph shows up the way I want it to. And then I'm creating a shaded region associated with the integral. So the part of the integral I want to consider, the integral values for t, that's why I'm using it for the integral values of t, is t naught to tf. The integral values I'm going to use for the velocity are just the evaluation of that function v, and I'm using the absolute value of it again because I'm plotting the absolute value. I'm looking at that last example. I'm creating a set of vertices to create a polygon region that has a certain shading. This will ultimately make a gray, slightly transparent region that will then be added as a patch. So this is using that polygon that I imported from Matplotlib. I then create some text to describe what's going on with this function. And then this is just getting rid of some parts of the plot that I don't want to appear. But you could turn these to true if you wanted to see what they do. So let's just go ahead and run this and see what we produce. So if you look at this right here, here's the plot of the absolute value of the velocity. It's 5 over this whole time interval here. It doesn't really matter what t naught and tf are. But I just show this. What we did when we compute 5 times tf minus t naught is we're getting the area of this rectangle shown in gray, which is what the integral is representing. The integral is representing actually the area of this rectangle. And if I just plotted v instead of the absolute value of v, and I looked at what the integral was, we know the integral actually is 0. And if you look at it, you have two rectangles, each of the same area, but one is above the y-axis and one is below the y-axis. So if you treat this like a positive area and this is a negative area and add them up, you get 0. So this is what we're seeing. The integrals are related to the areas of these shaded rectangles. And in particular, the integral of the absolute value of v is exactly the area of the single shaded rectangle we showed. On the other hand, the integral of v is given by the area of the rectangle above the time axis, the t-axis, minus the area of the rectangle below the t-axis. They appear to cancel each other out. And this is what I was just saying in the video. If we think of areas as being signed, so that any area above a horizontal axis is positive, while any area below the horizontal axis is negative, then we see that the integral is actually the sum of the signed areas. These observations actually lead us to a useful conceptualization of integrals in terms of sizes of positive and negative regions of a function over a set. So below, what I do is visualize what the sign of an integral is for a function in terms of what dominates, either the positive or negative areas. The quad function, and then I use the quad function to compute accurate approximations of the integral. I'm going to fix that there. Well, I'll fix that later in terms of how that reads, so it reads a little better. Let's talk about the quad function that's available within SciPy, and I provide some linking here. The quad function is within the integrate subpackage of SciPy. You should spend at least 5 to 10 minutes to review some of the documentation at this link. I'll click on it now to show you it is rather substantial. They provide some nice description. I mean, there's a lot of parameters, a lot of things that go into this. I'm going to show you how to use it easily. But then they also provide some examples below. There's a good number of examples here. And you could try implementing these in the notebook for yourself. The quad function returns a tuple as an output. It's much like our compute bisection function from the previous lecture notebook in that way. The first component is the approximation of the integral. The second component is an approximation of the error in the integral, because it's only, an approximation of the error in our approximation of the integral. Therefore, we usually append a 0 in square brackets to the end of our calls to the quad function, so that if we're just interested in the actual approximation of the integral. So you'll see this below. For instance, here, when I want to approximate the integral of a function using quad, I say integrate f on an interval from a to b, and then just return to me the approximation of the integral. And that will give me the integral of the function over a to b as an approximation. So that's how easy it is. That's about as much calculus as you need to know to use the quad function. You give it a function f, you give it the limits of integration, a to b as an interval, and then you use that 0 in square brackets, and that will return you an approximation of the integral of f over the interval a to b. If you peruse the source code for the quad function, then you will see some nice doc strings and doc test. For instance, let's click it here. Here, look at this nice long doc string to really read, to explain what's going on. And they even have some, let me go up here. I think there's, yes, right here. Here are some tests. Oh, wait, no, excuse me. Those are not tests. Where are the doc tests? I saw them somewhere here. Here we go. Examples here. These are doc tests that should run. So the integrate subpackage itself is also rather interesting and useful to familiarize yourself. So I won't bother with clicking it here and showing the video, but you should see there's other integration functions you might be interested in looking at as well. So we import quad from SciPy integrate, and I'm just going to call it quad whenever I want. And now I'm going to create a plot integral function where the entire computation for approximating the integral is done by the call to quad. So it's this one line of code. Everything below this is just plotting. I'm giving a set of x values on which to construct the plot and a set of y values. So that's where I want to plot the function, and a to b is the interval that I want to compute the integral of f. So I might want to compute the integral on a subset of values from x min to x max. You'll see what's going on when I do this here. Then I'm just plotting a typical x-axis and doing some other stuff, shaded regions. So the integral points for x and the integral points for y that I'm plotting to create my patch, my polygon patch that shades in the region that shows the integral I want to approximate. That's given by these points, and I'm using I to denote these are integral points, or points that are related to the integral that I'm trying to plot and visualize. So I'm just going to go ahead and interact with this plot integral function with a function f that is given by x plus 1 times x minus 5 minus sine of 3x. I am going to plot it from -1 to 5, and then I'm going to use different a and b values that I move around with a float slider to describe the integral on a particular interval of a to b. So here's my function from -1 to 5. So it's in the red curve. So I'm going to try to zoom out just a little bit so that you can see more of this. There we go. I'll have to do one more zoom out. There we go. So here's this red curve, which is the function I'm plotting from -1 to 5. And my a and b are 2 to 4. So I'm just showing here a and b, they're 2 to 4. I'm just labeling them as a and b though. And you can see in the gray region, that's the region, that's the signed area that I want to approximate. So the integral from a to b of f of x dx for this value of a and this value of b is approximately -1.72. Now, is the sign of it correct? Does it seem reasonable? Well, if you look at the amount of gray that is above this x-axis, this horizontal axis, it certainly seems less than the amount of the gray area that's below the x-axis. So it certainly seems reasonable that this value is negative. Now, if I increase b a little bit, so I increase b just a touch to move over here, I should accumulate more positive area, and while it will probably still be negative, it should be something that's greater than -1.72. So let's see if that's correct. 4.1, -1.53. That is greater than -1.72. I've accumulated more positive area. And if I increase a little bit more to 4.2, you see it went down again. I accumulated more positive area. Whereas if I make b, look what happens if I increase b more, I'll start to get more negative area, and this value should start to decrease. -1.55, there's now some more negative area accumulating. -1.71, more negative area is now added. And now -1.92, more negative area. So you can play with this slider, and you can move b down to, let's say, 3.9, but now imagine that I move a up to like 2.9. Now the value is positive, 2.86, because this amount of area above the x-axis outweighs the amount of area below the x-axis. It's just more. So when I add the two together, the positive and negative area, the overall result now is positive. How do you compute that? With the quad function. You don't have to worry about it. This is the amount of calculus you really need to understand to run this part of the code, is that the quad function is just computing the integral for you, at least an approximation. Now, context is everything here. I'm going to enlarge my screen a little bit so that everything's bigger and easier to read. We have just looked at functions with univariate inputs, meaning a single input. Subsequently, we observed that the integral is related to the signed area between the curve defined by the function and the axis defined by the input. This observation can be conceptually extended to functions with multivariate inputs. Suppose f of x is a real valued function, but x is actually a point in the Euclidean plane. Then for a set of numbers in R2, the integral of this function is related to the signed volume between the surface given by the graph of the function over the set A and the horizontal plane defined by the two-dimensional input. And you can have signed volume because if it's above the plane, you would call it positive volume, and if it's below the plane, you would call it negative volume. Now, you can generalize the concept of area and volume to describe integrals in geometric terms when the inputs are three-dimensionals or higher, but we really need to say like what that means. So, and we're not going to get into that really here. We can pretty much stick with one-dimensional examples to explore the typical numerical algorithms used to estimate integrals, although some of the strengths and weaknesses of these algorithms are not apparent until we get to higher dimensions, and you should keep that in mind. There are a lot of algorithms to perform numerical integration, and I provide a link to a Wikipedia article that shows some of the numerical integration algorithms that are very common. We are first going to discuss geometric or deterministic methods. Many of the deterministic approaches to estimating integrals are based on partitioning the set A, meaning to cut up the set into non-overlapping collections of subsets, although we do allow for shared boundaries. And then we do this such that the signed areas, or volume, or generalizations of that in higher dimensions, between the graph of f of x and these subsets drawn on the horizontal axis, or the plane, or the hyperplane if you go to higher dimensions, defined by the inputs are well approximated by a simple geometric object for which we know the area, again, or the volume or generalization of the volume. Some key points. The simplest such methods for 1D problems involve the use of rectangles or trapezoids, where the areas are easily computed from rules we've learned in geometry. When A is simply an interval, we typically choose the partition of A to be equally sized subintervals, and we approximate the signed area of f of x over each subinterval by simply using a rectangle that is as wide as the subinterval with height given by the evaluation of f of x at some point in the subinterval. Now, how you choose to evaluate f in that subinterval is often related to certain choices of rectangle rules. Adding up all of the signed areas then ultimately give us our approximation to the integral. So I show this below and we'll go through it real quickly, but not too fast. We're not going to rush, but it won't take too long. As a suggested activity, I think you should add a useful docstring here and a doc test. And that might be useful after watching this video and playing around with this code yourself. So I'm first just going to run this code, which is it creates a compute rectangle rules, and we're going to consider 3 types of rectangle rules. Ones that are the left, the right, or the midpoint rules. This just means do you use the left endpoint of a subinterval to evaluate the height of the rectangle, the right endpoint of the subinterval, or the midpoint of the subinterval. That's it. So what we do is this function takes a function f that you want to integrate. It takes a to b, and n is the number of rectangles you want to use. So we use linspace to say, okay, from a to b, create n plus 1 points in order to create our n rectangles. And then we say this is what the length of the base, the width of each rectangle is. It's just ix1 minus ix0. I only need to do that computation because these are regularly uniformly spaced points. Then the height of the rectangles is either determined by the evaluation of the function at the left endpoints, so I use some index slicing here, the right endpoints, notice I start my indexing at 1 and go to the end, or midpoints, and notice here I'm doing slicing and then I'm offsetting all the input values by half of the distance of the length of the subinterval in order to get the midpoint. That's it. This is an entire way to code up 3 different ways to approximate an integral. Well, there's one more part, which is I then use the sum function to sum up all of the heights times the width. So this is then a simple way to compute all of the areas of each rectangle and add them up in one line of code. So it's not that complex of a function, but it does create 3 different types of approximations that you can choose using this rule of an integral. So we've run that. Now let's do some experiments. So below what we show is the following. We use the compute rect rules function defined above with the default rule, the left endpoint. So I don't even use this initially. That's a default value, so I'll just focus on f, a, b, and n. I will analyze the rate of convergence, ROC for rate of convergence. And then I will create interactive visualizations of this function that help us tell a story about the integral. So here's that function f we saw before, this lambda function x plus 1 times x minus 5 times sine of 3x. Now, let's look at an approximation of the integral with the rectangle rule, the left endpoint rule, when we have a is 2, b is 4, and n is 4. So we're going to use 4 integrals, and we're going to print this approximation. Now, look at what I return. Let's just talk, I skipped over that. We return I sub x, delta sub x, I sub y, and the integral approximation. I return all of these things because some of these are useful for plotting, as I'll do later, but I only want to look at the integral approximation, so I want this fourth output. Because Python indexing starts at 0, I use 3. So that returns the integral approximation, and we look at it, and we get negative 1.52588 and some additional numbers. Now, is that a reasonable approximation to the integral from 2 to 4? Well, recall here, when we make A 2, and we make B 4, we got negative 1.72. So negative 1.52, it's kind of close to negative 1.72. It at least has the right sign in that it's negative, but it's not as close as perhaps we would like. So to study the rate of convergence, how quickly this rule gets to a better approximation, gets to the true value, and we'll just go ahead and treat the quad value as if it's treating the true value. We usually vary critical inputs over orders of magnitude and employ log-log plots to understand how errors are reduced by refinement of the inputs. So here I use the log space function within NumPy to create an array that varies over various orders of magnitude. The code below creates ends that go from 10 to the first power all the way up to 10 to the fourth power. And I'm saying how many points I want. So this is creating my ends. Now, so now you see, right, I'm going to use 10 rectangles, 100 rectangles, 1,000, and 10,000, right? So I could have changed this, like, what's the first one going to be? This 10. Negative 1.7, that's already pretty close to negative 1.72. But if you look at this, notice there's 10 point, 100 point. If you look at that, those are floats. But we need these to be ints because this argument to linspace is supposed to be an int type. So given that, we have an easy fix. I'll create my log space again, and then I will cast it as type int. Now when you print, you notice you don't have the point there, that decimal point. These are now of type integer. I've cast them that way. So now let's create a list of approximations for increasing numbers of rectangles. So I made an empty list here, and I append to it the rectangle rule, the left-hand rule approximation, with these differing n values where n is being chosen from this array of n's. And then here's my approximations. Negative 1.7007, negative 1.722, negative 1.721, and again, negative 1.721. And then there's the change in these decimal points. Now, these look like they're getting to be a better approximation relative to the quad. If I wanted to actually compute the errors as a function of increasing numbers of rectangles, then this is what I would do. The errors from my left approximation are, I take that list and I turn it into an array. So np.array int approxes. So now I have an array of these. And I subtract off the value from the array. So when I subtract a constant from an array, it gets subtracted from all of the elements. So this will tell me what all of the errors are. And I see, yes, it's about 0.02 off, right? Negative 1.7 compared to like negative 1.72. It's off in that decimal place, which is given by 2, and then this is 10 to the negative 2 here. And then you see that the order, the magnitude of these is shrinking as we increase the number, as the n values increase. So now we visualize the convergence of the left-hand rule. So I create a figure. I use a log-log plot because I used a log scale for the n's. And now when I look at this plot, so then for those log-log of n's, and then you have to use the absolute value of the errors because some of these are negative. And a log-log plot is going to take a log of these values, and you're not allowed to take logarithms of negative values. So you take the absolute value of the errors, and then when I plot this, you see something that looks like a straight line, and you can actually start to see you could imagine that you'd want to estimate a slope of this line. So let's look at this. How can we estimate the actual rate of convergence? How fast is this rule converging? Well, the above curve is approximately a straight line. We can fit a line of best fit below and report the slope of that line. Remember the polyfit. The polyfit is taking our inputs, these are our x values and our y values, and that are the values that were plotted here. And now we're saying fit a polynomial of first order to it, and this argument right here will return the slope of that value, of that line. So what is the slope of that line? It's about -1. How to interpret what that means? This tells us how many orders of magnitude the error is decreased for every order of magnitude increased in the number of rectangles, which means if you go from 10 to the second to 10 to the third number of rectangles, you expect to reduce your error by a single order of magnitude, by -1. If I did a two orders of magnitude increase in the number of rectangles, I expect 2 orders of magnitude decrease in my error, because it's a 1-to-1 correspondence, and the negative says the error is decreasing. Let's do some fancier visualization. So I'm going to plot the rectangle rules now so you can see what the rectangles are doing and how this method works. So now I'm going to use all of the outputs from compute rectangle rule, not just the integral approximation, because I use these for outputs. I'm also going to use the quadrature rule to get a reference value, and then everything else below here is just plotting. And I think at this point, hopefully people can read it. There's, I'm creating like axes and some patches and collections, but the computations are just here. And then this is stuff you can play with and see how to, mess with the options to make the plots look however you like. So that created a function to plot the rectangle rules. And now I'm going to interact with it. And I'm also going to allow myself to choose different rules. So I fix the function, and I'm letting other things vary. I'm fixing values for the plotting as well. So let me run this. And let me again kind of zoom out a little bit so you can see the whole shebang here. So when n is 3, which is my default, you see 3 rectangles. And you notice the value of the function, right, that it's choosing for the height of the rectangle is at the left endpoint of this subinterval. It's at the left endpoint of this subinterval here. And for this third subinterval, it's again this left value. So it's using the 3. And so 3 is providing a pretty bad approximation of -1.72. It's giving me -1.35. Now it's negative, but it's off quite a bit. Look what happens if I use the right endpoint. It's even worse in this case. So now it's using the right endpoint of this function to evaluate this, to get the height of this rectangle, the right endpoint of this of the function on this subinterval to get the height of that rectangle, and again the right endpoint here. I think I might have said right in the previous one, but it was left. And then the midpoint, notice it's using a midpoint of the subintervals to create the height of the rectangles. That's the only difference. And that's -1.94 now, which is better than what the other ones were. And then, so I'll shrink that down. If you increase the number of rectangles, watch what happens. So if I go to 4, it's, not much better, but it's a little better, I would say, from -1.35 to -1.53. If I use 5, maybe a little better. 6 seems a little better. So 7, 8 rectangles, 9, 10, 11, 12, 13, 14, and I'm just going to go up to a larger number. And you start to see what happens as you increase the number of rectangles. At this point, with 44 rectangles, you see that it's doing a pretty good job of approximating the region under the curve from A to B. And then the rectangles here have negative area, the other ones are positive. You add them up, and it's very simple to add up areas of rectangles, and that's all we're doing here. And if I choose the right endpoint, at this point, it's also very accurate. The midpoint is also very accurate. And it's harder to see the changes when you have a lot of them. It's easier to see them when you have, fewer, like 6. And you can see those are the midpoint ones, the right-hand rule, and the left-hand rule. And for a different function shown below, this is just x squared. Here is a quadratic. Here I have my A and my B, and here I'm using 10 rectangles initially with the left rule. Notice it's underestimating the area. That's actually 0.33, the integral from A to B, and it's approximating it as 0.29. If I use a right rule, then I use the largest value of the function on each subinterval, then it overestimates. And if I use the midpoint rule, it looks like it nails it just about right away because it over and underestimates by about the same amount in ways that cancel out on either side of within the subinterval. And you can again you can increase. Oop, I'm not plotting it as far as I should. Let me shrink that down. So there you go. I'll do that a little bit more gradually. There we go. And then if I increase the number of rectangles, you'll again see the convergence. And the middle is going to look better. But here we go. With the left-hand rule, it's underestimating. But now watch as I increase the number of rectangles. It should, here, I'll just go to a larger number. Go to 300 rectangles. It's hard. They plot almost like it's very smooth. So maybe that's too many. Let's go to like 50. Right? So it's close. It's 0.05 away from this answer at this point. So, okay, this leads us to an activity on rectangle rules. You should feel free to create many new code and markdown cells below as you work through this activity. What I want you to do is create a wrapper function called multiple underscore rect underscore approximation. Which has all the same parameters as compute rectangle rules, except that the in parameter is now assumed to be an array or a list of integers containing different numbers of rectangles for which the approximate integrals should be computed. This wrapper function should then loop through all the values in the list of in values and then compute the compute rectangle rules to obtain the associated approximate integral and store all of the approximate integrals in a list that is returned by the wrapper function. So you could do this by just wrapping around compute rectangle rules. And all you need to do is just, like what I did here, where I created this function here, I'm just wrapping around compute rectangle rules. Imagine you create a function that does something like this, but also allows you to choose the rule as well. And, like here, like this takes the rule as a parameter in the plot rectangle rules, and notice that it's used as the input here so that you can change it. That was what I was doing in the plotting. I'm going to zoom in to make everything look a little bigger again and easier to read. So it's not as complicated as it sounds. I'm just trying to be very specific about what I want you to do. For a number of different lambda functions, including the function f given by just the identity function, f of x equals x and f of x equals x squared, and at least one more of your choosing. At least one more. I recommend choosing 2 or 3 more. Compute the errors for the left, right, and midpoint rule approximations for n, for 10, 100, 1000, for a equals 0 and b equals 1, and store the errors as either a list or numpy array. And I give a hint on how to compute the errors. And you can also use the code I had above as a template. Now for each of your different lambda functions, create a separate log-log plot with a legend that shows the errors for each rectangle rule approximation versus the number of rectangles. Meaning each of these log-log plots should show the error in the left-hand rule, the error in the right-hand rule, and the error in the midpoint rule for a fixed function. So however many functions you used here, you create that many log-log plots, and in each plot there's 3 curves of these errors, showing the error in the left, the right, and the midpoint rule. And then you need to analyze the rate of convergence, and I want you to estimate the rate of convergence using the polyfit function as shown above. And then I want you to comment on and interpret your results in the markdown cell below. That would be this cell right here. Some questions you should try to answer are the following. Which method appears to be the most accurate or converge the fastest? Why do you think that is? A hint is to create visualizations of the approximations of integrals with a small number of rectangles for the different methods. And I kind of hinted at this above in terms of the midpoint rule having some cancellation of errors. Some brief research online will also reveal the answer. So I'm going to stop this first video here. The next one will be on Monte Carlo integration, and it won't be as long as this video. Thank you for listening.